In the previous lessons, we learned about equilibrium constant, and we used the letter K to represent it. And today we are going to relate K to something called reaction quotient, which is Q. And Q is the ratio of product to reactants, but here's the main difference. It is at any point. It doesn't have to be at equilibrium in a chemical reaction. So here I have my basic example of a chemical reaction. And of course, we assume that this is going to be a reversible reaction. And I have my A plus B reactant equal to C product. And the same thing, the way we write K before, is product over reactant in terms of concentration. And just like we write for K, we also ignore solid and liquid. Now, let me just write the K in this case for this reaction. Of course, I would have my product C over the reactant, which in this case A, and of course the little letter, the lowercase, that would be the coefficient of your reaction. And here we have another reactant called B. Now let's combine Q and K together. Well, first of all, we need to realize that both of them will equal to our values, and we can draw a number line. And at equilibrium, which is somewhere in this right here, somewhere in the middle, you would have K, okay? And the quotient would be anywhere. K is at equilibrium, okay? This will be your equilibrium. Keep that in mind. Let's look at Q. It is product over reactant. So if this is happening at the beginning of the reaction, do we have any product at all? So basically, if we have the starting point for Q, if Q equal to 0, what does that tell you? That the number of the product is equal to 0, where the number of reactant will equal to a number. And that is the mathematical explanation how Q equal to 0. But this number right here, what does that number represent? It is the number of reactants. So here you have all reactants, okay? Where Q is equal to 0. But let's take to the other side where it's not equal to 0, which we know is going to be an infinitely large number. So this is a very large number. Okay. Now, how does that work? Well, first of all, when a reaction occurs over time, guess what happens to the values of the reactant? So we can tell that the number of the product will go up really, really high, but the number of reactant will go down really, really low, to the point that's almost near 0. So that's how we get this large number. So now let's combine Q and K together. Well, if Q over here, from in this range right here, okay, if Q is what? Is less than K, guess what happens? See how Q is 0? Somewhere around here will be less than K. If this to be a reversible reaction, our chemical reaction will naturally favor this direction. We want to get to equilibrium. That's the nature of all chemical reaction. So what does that mean? If it's going to shift toward this way, it's going to favor making product. Just like we had before here. All the way over here will be all product. So in this case, this would be favor the product. But what if our Q is somewhere over here? So let's just say our Q is somewhere over here. And if Q is somewhere over here, which is going to be greater than K, so Q is greater than K, what do we have? We would have the reaction naturally would try to shift toward equilibrium. And if we look at the arrow, which going toward equilibrium, we know that it is favored in the direction of reactants. So it's going to make more reactants. And that's how you relate Q and K and determine which direction the reaction is going to favor. But what happens when you have Q equal to K? Of course, at this particular point, it is at equilibrium. And that's how you relate Q and K to determine which direction is going to favor.